Hello and welcome back to C++ real-time audio programming with Bela. I'm Andrew McPherson, one of the original creators of Bela, and in this course we'll be taking you through the skills that you need to create the components of synthesizers and audio effects and implement them in C++ on embedded hardware. For those just joining us, these are some of the programming topics we'll cover in this course. And each of the programming topics will typically be associated with one or more music or audio topics. For today specifically, we're going to be looking at working with buffers and arrays, and the examples we'll create will be those that play back pre-recorded audio files. Specifically, today we'll look at the Bela C API, looking at some of the functions and data structures that you need to create C++ programs on Bela. We'll also look at working with buffers or arrays in C++, and we'll make an example that plays a sound file loaded from the storage on the board. You can find companion materials for this lecture, including code examples, at the GitHub link at the bottom of this page. If you're just joining us, you'll want to have a Bela starter kit or a Bela mini starter kit to follow along with the examples. For some future lectures, there are also some basic electronic parts that we recommend having, though you won't need any of these for this lecture. More details about this can be found in Lecture 0 in this series. Also, if you're just joining us, be sure to update your Bela software to the latest version. You can get the latest version from learn.bela.io/update, and we recommend updating it through the browser-based IDE. Again, you'll find more information about updating your board in Lecture 0 in this series. Let's start with a brief recap of the last lecture. We were talking about the way that real-time audio systems process audio not one sample at a time, but in blocks of samples. The idea being that by processing several samples at a time, we can make our system more immune to the natural timing variations of operating systems that are running several different tasks at once. And as we saw last time, one of the signature features of Bela is that its real-time operating system allows us to use much smaller audio block sizes than most operating systems, and this translates to a much lower latency or delay between input and output. Now, the general idea of processing audio in blocks is that at any given time, while the audio hardware is playing one block, our processor is busy calculating the next, so we're always trying to stay one step ahead of the hardware. Within each of these blocks, of course, we see a group of samples, the idea being that when we run our render function on Bela, our goal is to process all the audio samples in the block and get out of the way as quickly as possible so the system can do the rest. In the last lecture, we saw that we wanted to generate a sine wave in real time, calculating one block at a time, like this. However, when we first got started, our initial real-time code produced something like this. The problem that we saw in the last lecture is that we had to remember the phase of the sine wave from one block to the next to ensure that our calculation would always pick up from where we left off rather than starting over again from the beginning. And this idea of remembering the previous state is an absolutely fundamental concept to real-time audio programming. Our code to do that looked something like this. We saw that we used a global variable to remember the phase of the sine wave, and the global variable is notable because it remembers its value between calls to the render function. Within the render function, we saw that we would increment the phase each audio frame, and then use the value of the phase to calculate the sine wave. When we first tried this, we found another subtle issue as G-phase became larger, which had to do with a loss of precision manifesting in a kind of stair-stepping effect in the frequency. What we did to solve that was to wrap around G-phase so that it always stayed in the range between 0 and 2 pi. Now in this example, we frequently encountered this variable called context, and we didn't really talk about this in the last lecture. We see that context is an argument to the render function, and that within render we use context in several different ways. So what is all this about? This takes us into the basics of the Bela C API. The first thing to know about writing a Bela program is that you should implement three main functions. There is a function called setup. This runs once at the beginning before the audio starts being calculated. There's a function called render, which is going to be called repeatedly by the Bela system for you to process the audio. And finally, there's a function called cleanup, which runs once at the end of the program. Each of these functions takes two arguments, one of type Bela context and one of type void star. The second of these we won't look at now. It's essentially an opportunity for you to pass a custom data structure into your program, but it's not something that we typically use in our examples. But let's have a look at this variable of type Bela context. The Bela context is a type of data structure known as a struct in C or C++. And this structure holds all sorts of useful information about how the system is set up. Things like block sizes, sample rates, and numbers of channels, and in fact, even the sample data itself. And crucially, the Bela contexts hold information not only on audio input and output, but also on the analog and digital IOs that you can find on the Bela board. What this means is that our render function doesn't have to worry about how to talk to the hardware. That's handled internally by the Bela system. Instead, all we need to do is pass samples to and from the Bela context data structure in order to read and write audio. Looking into this in more detail, you can find a complete list of what's included in Bela context inside the Documentation tab in Bela's browser-based IDE. You can also find this information on the Bela knowledge base at learn.bela.io. Just a few examples of what's found inside the Bela context data structure. There are buffers to hold the audio input and audio output samples. There are variables to hold the number of audio frames, the number of input and output channels, the audio sample rate, and many other things. And the idea is that all of this information is passed to your render function by the Bela system every time it's called. Render gets a pointer to this data structure. What this means is that this data structure lives in memory somewhere, and the Bela system will tell us where to find it. We'll talk more about pointers in a later lecture. But to access elements inside of the Bela context data structure, we use this arrow operator. So for example, context dash greater than audio sample rate means access the variable audio sample rate inside the Bela context data structure, in this case returning a value of 44,100. So then, if we look back to our code example, we can see that context arrow audio frames in the default settings would return a value of 16, leading that for loop to be run 16 times within render. Context audio sample rate would have a default value of 44,100, and this would be used to calculate the amount of phase increment needed to make the sine wave sound at the right frequency. Context audio out channels would have a value of 2 because Bela has stereo audio output. So now let's move to our next topic. In this lecture, we want to play a clip of pre-recorded audio that's stored in a WAV file on the board. Now, we're not going to worry just yet about how we load the sound off of the storage into memory. Instead, we're going to assume that we have loaded it and that it is stored in a buffer or array in memory somewhere. When we talk about arrays, all we really mean is a series of values of a particular type stored one after another in memory. We can declare arrays with a syntax like this, using square brackets to tell us what the size of the array is. Notice that this is an array of type float. And we can also use square brackets to access the individual elements of the array. Notice that the array indexing starts from 0, so if we had an array with 24 elements in it, the last element would have index 23. There are other ways to work with arrays. In C++, a more full-featured version of the array concept is a data structure called a vector. Notice that this is declared std : vector, and then the type in these angle brackets. We'll talk more about this syntax later on. But the question in the meantime is that given that we have a pre-recorded audio clip stored in a buffer in memory, how do we play this back in real time block by block? We're going to need some other information to remember where we were in the playback to ensure that we can always pick up where we left off. What kind of information would that be? Well, think about what happens in a typical audio editor. We have a playhead. The playhead shows us where in the sound file we're playing at any given time, and when the sound file plays, the playhead moves forward at a constant speed. The analogy here in programming is that the playhead is going to keep track of where in the buffer we are reading samples from at any given time. And so analogously to the previous lecture, the read pointer is also going to need to be a global variable so it doesn't forget its value between calls to render. So when we play the sound file, the contents of the buffer won't change. However, the read pointer is going to move as we play it. Now this may be conceptually straightforward, but it quickly becomes quite subtle when working in real time, basically because it's easy to lose track of what index means what. We actually have not one but two different kinds of buffers to think about. We have the buffer or array which stores the recorded sound, which we saw in the previous slide. We'll call it the source buffer. There's only one buffer of this type, its contents don't change, and the question is, how long is it? The answer is that it depends on the length of the sound that we just loaded, but it could potentially be quite long. There is also a buffer inside the render function which corresponds to each real-time audio block. This is the block-based processing that we saw at the beginning of this lecture. And each time render is called, you will get a new buffer which you can access via this function called audioWrite. We'll come back to that in a moment. Now, what is the length of this buffer? Well, that depends on the system audio block size, which you can set in the Bela settings. By default, Bela has a block size of 16 samples. Now what that means is that we are going to be systematically copying 16 samples at a time from our source buffer into our real-time audio buffer. And so we're going to need to keep track of actually two different indexes. One of them is our playhead or read pointer that tells us where we were in the original sound file. And the other one is where in the particular buffer corresponding to this call to render are we writing the output. Now let's look at this in a diagram. So here we have our source buffer at the top with our read pointer in green that tells us where we're reading the sound from, that's our playhead. And then in our real-time system, each call to render corresponds to one of these blocks. And for illustration purposes here, I'm assuming that there are 8 samples per block. The red pointer here indicates where we're going to be writing within that particular audio block. And we've seen in previous examples that we typically write a for loop inside the render function involving this variable called n, which starts at 0 and goes up through the number of audio frames. So what we're going to do initially is we are going to move the read pointer forward, copying samples from the source buffer into the real-time buffer. And during this process, n is going to go from 0 to 7 at the same time as g read pointer goes from 0 to 7, like so. So when we finish this, we will have copied the first 8 samples from the source buffer into our real-time audio output. Now to copy the next 8 samples, it's going to happen in the next call to render. And this time, we need our read pointer to start where we left off, i.e. pointing to sample number 8 in the original source buffer. But of course the value of n is going to reset to 0 because we're going to fill a new buffer in our render function, like so. And the same thing will happen in the third call to render. We need to remember where we left off in our original source buffer, but we're going to reset our variable n back to 0 and again copy 8 more samples into this new buffer in this third call to render, like so. And this will go on indefinitely until we reach the end of the buffer. Now there's a practical consideration here because we will eventually reach the end of the source buffer and fall off the end. This is a real problem because it'll mean that we're trying to access a part of memory that our program doesn't actually own. Now this is called a segmentation fault, and it's one of the most common ways that programs crash. We actually want our program to crash when this happens because what it means is that our code has tried to access a piece of memory that it doesn't own. If the program didn't crash, the implication would be that our program could read any memory whatsoever on the system, which would potentially be a huge security hole because it would mean that we could read things that other programs or even other users on the computer were doing. But of course, we don't want our program to crash, and so we have to avoid falling off the end like this. So what should we do instead? Well, a few options. We could simply stop playing, no longer move the read pointer and make sure that we don't read into the source buffer any further. We could also return the read pointer back to 0 and start playing all over again in a loop. So we're going to do it that way. This brings us to our first task. In the companion materials for this lecture, you'll find an example called Sample Player. Now this is partially implemented. It loads a sample from the storage, and it's up to you to write the code inside of render to implement the playback of the source buffer. So what I want you to do at this point is pause the video, see if you can implement the copying of samples from the source buffer into the real-time audio output, and have it return to the beginning of the sample buffer whenever the read pointer gets to the end. Okay, let's look at how this goes. I've pulled out the most salient bits of the code here. We have some global variables here that we need to keep track of the source buffer, where the sample is loaded, and also our read pointer or playhead that tells us where we're playing from. Again, remember that gReadPointer needs to be a global variable because we need to remember where we were between calls to render. Inside the render function, we have this for loop that's going to become quite familiar in these programs. This runs once per audio frame within the block, which is a default of 16 times. Within the for loop, notice that we have this variable called n. N is what starts at 0, it goes up to, but not including 16. And we're also using this variable n to tell Bela where to write the audio sample in the output buffer. Notice that when we're loading things from the sample buffer, we're not using n, we're using gReadPointer. This is the playhead that we want to use to figure out where we were in our longer sound file. And this is how we move the playhead between each audio frame. We increment gReadPointer each time, and then we check if it has reached the end of the buffer, and if so, we reset it to 0. Notice that we can get the length of the buffer by using gsamplebuffer.size because this is a C++ vector class. We'll talk more about this later on. Okay, so here we have our sample player example. You can see it's loading the file called slowdrumloop.wav, which is stored here in the project directory. This is an example from freesound.org. You can find where it comes from here. And let's just run that now and hear what it sounds like. So we'll build the project and then run. Okay, so there we go. That seems to work as expected. Notice that you're hearing a mono file. It should sound the same in both channels, no stereo image whatsoever. Now there's one other bit of the Bela API we haven't looked at yet here, and that's this function called audioWrite. What is this doing? Well, audioWrite is essentially a convenience function that is helping us store samples inside of the audio output buffer. audioWrite takes 4 arguments. The first one is a reference to the Bela context structure. We need this because what we're going to be doing is storing audio samples inside of this structure somewhere. We have to indicate the frame where we want to write. This is essentially saying which of the 16 time slices within the buffer do we want to write. Bela by default has a stereo audio output, so we need to indicate which channel we intend to write to, and then finally we need to indicate what the value is. The typical range of values is between -1 and 1. So here's a typical example of how we might call this function, and my question for you is which of the samples within the structure are we going to be writing? Well, we're going to be writing frame 3, channel 1, which corresponds to the right channel, so we're going to be writing the slot labeled R3 here, and we're going to be storing a value of 0.5 into it. If you dig into the Bela core code, you'd find the implementation of audioWrite looking something like this. And what you can see is that we're storing a value inside of this buffer called context arrow audio out. And there's this formula for calculating which index we want to store at. So the question becomes, can we work out how the audio out buffer is organized based on the code that we see here? Now the key point is that audio out inside Bela context is a one-dimensional array, i.e. it's just a set of float values organized one after another in memory. But the funny thing is we have potentially 2 or more channels of audio stored within this single-dimensional array. Now there's a couple ways of doing this. One of the ways we can store multiple channels within a single-dimensional array is what we call a non-interleaved format. We would start with all of the samples for the first channel, followed by all of the samples for the second channel. The advantage being that you get one contiguous block of samples for each channel, these blocks organized one after another in memory. The other format that we'll encounter is what's called interleaved. The idea is that we store everything for the first frame first, followed by everything for the second frame, everything for the third frame, and so forth. And so we're actually alternating between left and right channels if we have a stereo buffer. So, here again is the code of what Bela implements. Can you work out from this whether Bela is storing this in an interleaved or a non-interleaved format? Well, the answer is that this is interleaved. And the reason we know that is when we increment the frame number, we're skipping ahead by the number of channels in the buffer. And I'll leave you to work out the rest of that formula if you're interested. Now let's take this opportunity to look at how we actually loaded the file off of the storage. What we used here was an example of a Bela library, a pre-made block of code that we've written that you can include in your projects. Now in the Bela IDE, you can go down to the very bottom tab here and see a list of all of the libraries that are installed on the board. These libraries cover things like working with common hardware sensors and various audio processing routines. So if we look at the audio file library here, we can see within this that we have everything that we need to include the library into our project, which involves this line starting #include. You could just copy and paste this into your render.cpp file. We also have a series of examples that use the library, and then you can see the code within the library by clicking on one of these files. Back to our example then, we're using the audio file library, and specifically we're using the function called audiofileutilities::load mono. And what this does is it loads a single channel from a WAV file and stores it into a buffer, which is a vector of type float. Okay, so there's a lot of colons and angle braces and various C++ syntax happening here, so let's unpack that a little bit. First of all, std::, audio file utilities : these are examples of namespaces, which is a particular feature of the C++ language. Basically, all we're talking about here is that we're adding a prefix to the names of these functions and data types. And by adding this prefix, we help avoid ambiguity and conflicts if we had a big complicated project that, for instance, ended up with two different things called vector or two different things called load mono. Now this function returns a vector of type float. A vector is basically just an array with some extra infrastructure around it. So notice that the float is in the angle braces. That tells us it's a vector of floats rather than, for example, a vector of ints. Vector here is one example within what's called the C++ standard template library, which is something that we can talk about in a later lecture. For now, suffice to say that we return this vector and we can check whether the file loaded successfully by seeing whether it's empty. To see whether it's empty, we check the size of the vector. If the size is 0, there's no samples, then probably there was an error, and what we want to do is return false from our setup function, which will tell Bela not to continue. The Bela audio file library itself uses an open source library called libsoundfile. Libsoundfile is quite a flexible library that supports not just WAV, but a number of other formats, notably not MP3, and this is not for technical reasons, but because of patent and licensing issues around the MP3 standard. If you wanted to load compressed audio, you could use, for example, the OGVorbis or FLAC formats. So now suppose that instead of playing a mono audio file, we actually wanted to play a stereo file. How do we do that? Well, first of all, stereo WAV files internally on the disk are stored in an interleaved format. In a sense, we don't care about this because the audio file utilities is going to deal with this for us. We're going to use a different function called load rather than load mono to parse the file and store it into a memory buffer. Now the function called load has a different return type. Instead of being a vector of type float, it's a vector of vectors of type float. And it's easy to get lost in all the colons and angle braces here. So what does this actually mean? What we're talking about is an array of arrays, or effectively a two-dimensional array. When we access elements within this two-dimensional array, we're going to use not one but two sets of square brackets. The first set of square brackets is going to tell us which channel we want to read from, and the second set of square brackets is going to tell us which frame within that channel we're going to read from. So for example, G sample buffer 0,100 says take the left channel and read frame 100 from the left channel. So in other words, we have taken an interleaved file off of the storage, we've loaded it, and we're actually storing it not in an interleaved single array, but in a multi-dimensional array in memory. And this is actually much more convenient for our audio code to work with. But to play it back, we're going to need to change the structure of our for loop so that instead of treating G sample buffer as a one-dimensional array, we treat it as a two-dimensional array, and that we store different samples in different channels of the Bela audio output. So that brings us to our second and final task for this lecture. In the companion materials, you'll find a project called Sample Player Stereo. This is very similar to the previous example, but the setup function has been changed to load a stereo file rather than a mono one. You need to change your render code to work out how to store different data in different channels of the audio output, and that may imply a different structure of the for loops compared to the previous example. So pause the video here, try that, and see if you can make it work. Okay, so let's look at the result here. Again, we are loading the file called slowdrumloop.wav, but G sample buffer now, instead of being a vector of type float, is a vector of vectors, a two-dimensional array, as we discussed. Setup has been changed to use this method called load rather than load mono. It'll now report the length of the file and the number of channels. We need to do our render function slightly differently, so you can see that we are incrementing the read pointer and wrapping it around more or less as we did before. The crucial change here is that we have to take the size of the first channel of audio rather than doing just G sample buffer.size. This is going to give us how many channels are in the buffer. We'll find that we have a size of 2. Instead, we say, okay, how many samples are in the left channel? The reason that this works is that we're making an assumption that every channel of G sample buffer has the same length. That's a good assumption for an audio file, but it's worth checking that that's actually true in the code that loads the audio file so that you don't get yourself in trouble. And then notice that the loading of the audio sample has been moved from this for loop into the inner for loop because we actually want to load a different sample for each channel of audio. So here we're saying take the output is going to be equal to G sample buffer of this particular channel of this particular frame. So this inner for loop is going to run twice for each frame, first for the left channel, then for the right channel, and we're going to pull the right sample out of this two-dimensional array and then write it to the appropriate place in the Bela audio context. So if you run this now, you should find that your drum loop has an appropriate stereo image compared to the previous mono version. Right, there we go. So there we have it, some code that loads and plays audio files from the Bela storage. A couple further considerations. One is that this approach won't necessarily work with very large or long sound files, because the BeagleBone only has 512 megabytes of RAM, so it's worth asking how much audio we could actually store in RAM, assuming that we were not using it for anything else. Well, one variable of type float is 4 bytes wide. What that means is that we could conceivably hold 128 million audio samples if we were doing nothing else with the RAM. Now, how long would that be at a 44 kilohertz sample rate? Well, assuming that we were working with a mono signal, that would be 128 million divided by 44,100, and that gives us about 2,900 seconds, or about 48 minutes of audio. So any file longer than this would not be able to fit all in RAM at the same time. There are alternative ways of dealing with this. The typical way of playing long files is actually to stream the file off of the storage. What this means is that instead of loading the whole file at a time, you're loading only small chunks as you need them, and then always trying to stay ahead, making sure you've loaded the right thing off of storage. Now, this is a more subtle operation because accessing the file system is not real-time safe. You can't load off of the storage inside your render function, you need a different thread. We can look at this more in a later lecture, but there is a Bela example called Sample Streamer that does this. And then finally, we've made the assumption that the WAV files that we're loading have the same sample rate as Bela of 44 kilohertz. If that's not the case, then we would need to think about resampling them either when we load them or when we play them back. And that's something that we'll see in a different form in the next lecture. Final comment for this lecture is that this idea of playing a buffer of sound over and over again actually has another name that you might be familiar with. It's a wavetable. And this can be a way of making an oscillator, that rather than actually calculating a sine wave every sample, as we did in the previous lecture, we might actually store a small buffer that held one complete oscillation of the sine, and then just play it back over and over again from that buffer. There are several advantages to this in terms of flexibility, because the buffer could have any shape whatsoever, and in terms of computational efficiency. Basically, we're talking about making a lookup table of output values for an oscillator, rather than calculating it from a mathematical function. And this is exactly going to be the topic of the next lecture, so stay tuned. Finally, when you're done, don't just pull the power. Remember to shut down the board gracefully using either the power button in the IDE or holding down the white button on the Bela cape. This is so you don't lose any data when you shut down. As always, here's our contact details, and don't forget to click subscribe so that you're notified of each new lecture as they become available. Thank you very much for following along, and we'll see you the next time.